Welcome to Professor Explains. Tonight, there is nothing you need to do, nowhere you need to be, no question you have to keep awake to answer. You can let the day go now, the whole weight of it, and let me do the talking. I am going to take you somewhere very old and very quiet and very cold, and we are going to go there slowly, the way you walk into a deep cave with a single lamp, letting your eyes adjust one step at a time. Imagine for a moment that you are standing in a small, cold room. It is white, and it is silent, and the light is dim and even. And in front of you, lying on a clean steel table, is a cylinder of ice. It is about as thick around as your arm. It is clear in places and milky in others, and if you bring your face close to it, you can see that it is not one solid thing at all. It is made of layers. Faint bands run across it, one after another, like the rings inside a tree trunk, except these are pressed flat and stacked, the way pages are stacked inside a closed book. Now, somewhere along that cylinder there is a single band, one layer, no thicker than a few of those tree ring lines pressed together. And a scientist years ago leaned over a length of ice very much like this one and put a finger near that one layer, and what that layer was quietly saying, once they had learned how to read it, was this: here the air over the North Atlantic warmed by as much as 16 degrees Celsius. 16 degrees. And it may have done so in less than a single human lifetime. In some places, the evidence suggests perhaps in as little as 10 years. Let that settle for a moment, not the fear of it, just the strangeness, the whole sky over a whole ocean, the cold breath of an entire glacial world warming by 16 degrees in about the span of time it takes a child to learn to walk and talk and start school. And the only reason we know it happened at all is that the snow remembered. The snow fell year after year, season after season, and it kept a record layer by patient layer of exactly how cold the air was when it landed. And then it froze, and it waited. For thousands upon thousands of years, it simply waited deep beneath the surface of Greenland, holding that single decade safe inside itself, until someone came with a drill and lifted it gently back up into the light. There is something almost tender about that when you think about it slowly enough. The planet keeps a diary, and we have only recently, in the long scheme of things, learned to read its handwriting. If you are lying somewhere comfortable right now and you feel like it, I would love to know where in the world you are listening from tonight. There are people drifting off to this voice in cities I will never see, in quiet houses in long beds by rain-streaked windows, and there is something warming about that we are all wandering down into the same old cold together. So leave a word in the comments if you wish whenever you wake, telling me where you are. And if you are new here and you would like more slow journeys of exactly this kind, you might let the subscribe button know. No rush, it will keep like the ice keeps. For now, just breathe and let me carry the rest. So, let us start with the simplest, gentlest question, and let us not hurry it. How does ice remember a single year? Think again of the tree. When a tree grows, it lays down a ring each year, a wider band in the good wet seasons, and a thinner one in the lean, dry ones. And so a tree carries its whole life written in circles, and you can count back through them, ring by ring, and say, this one was the summer my grandmother was born. Snow does something very similar, but it does it lying down in flat sheets one winter at a time. Up on the high ice of Greenland, snow falls and never fully melts away. The next year's snow falls on top of it. And the year after that, and the year after that, until the weight of all that snow above presses the snow below into ice. Slowly, the way a great many soft pages, stacked high enough, will compress the pages at the bottom of the pile. And because each year leaves its own thin signature, a layer that fell in the cold dark and a layer that fell in the brighter, slightly warmer part of the year, those layers can be counted. Near the top of an ice core, where the bands are still fat and unhurried. Scientists can count them one by one, exactly as you would count tree rings, and say with real confidence, this layer fell this many years ago, year by year. A calendar made of frozen weather going back not hundreds of years but tens of thousands, and in the deepest cores much further still. And here is the part that I find quietly wonderful, the part worth slowing right down for. The ice doesn't only count the years, it records what each year was like. A single layer of old snow is not blank. It is a little time capsule, and it has packed several different messages inside, and once you know how to listen, you can hear several things at once about a year that ended before any history book began. The first message is the one I mentioned. It is written in oxygen. Now I am going to ask you to follow one idea, and I promise to walk it slowly because it is the key that unlocks everything else, and once you have it, the whole rest of the night will open up easily in front of you. The idea has a name that sounds technical, D18O, which scientists say as Delta O18, but underneath the name it is really very simple and rather beautiful, and I want you to picture it rather than memorize it. Water, the water that becomes snow, is made of oxygen and hydrogen, and oxygen, it turns out, comes in slightly different weights. Most oxygen atoms are a little lighter, a few are a little heavier. They are exactly the same kind of thing, they are still oxygen. But some of them carry a touch more weight than the others, the way two apples from the same tree can be the same apple in every way, except that one is just slightly heavier in your hand. The lighter oxygen is the common one. The heavier oxygen is the rarer one, and it is the heavier one that scientists label oxygen-18. Now picture the ocean evaporating under the sky, lifting water up into the air to make clouds, to make snow, to fall on Greenland. The lighter water, carrying the lighter oxygen, lifts more easily. It is quicker to rise, quicker to travel. The heavier water, carrying that rarer heavy oxygen, is more reluctant. It is a little harder to evaporate and a little quicker to fall back out of the clouds as rain along the way. And here is the quiet magic of it. When the world is cold, properly deeply cold, an ice age kind of cold, that heavy water has an even harder time making the long, cold journey all the way to the top of Greenland. So the snow that finally falls there in a cold year is made of relatively more of the light oxygen and relatively less of the heavy. And in a warmer year, a little more of the heavy oxygen manages the trip and ends up frozen into that year's snow. So the ratio of heavy oxygen to light oxygen, frozen into a single layer of ancient snow, is a thermometer. Not a thermometer with a glass tube and a red line. A thermometer made of the snow itself. A low ratio of heavy oxygen. That means colder air the year that snow fell. A higher ratio, that means warmer. Each layer is a reading taken automatically by the sky on the day it snowed and then sealed and stored and forgotten for 50,000 years until a careful person melts a sliver of it and measures atom by atom how heavy its oxygen is, and reads the temperature of a vanished winter. That is the thermometer frozen in the layer. And once you truly have that picture and a single band of old ice quietly holding the temperature of one long dead year, you can begin to understand how anyone could ever stand there and say, here, the air warmed by 16 degrees, almost overnight in the language of the earth. But the oxygen is not the only message in the layer. The snow carries other things too, and they all agree with one another, which is part of why scientists came to trust what the ice was telling them. A cold year and a warm year do not only differ in their oxygen, they look different, they feel different, frozen into the core. A cold, glacial year is a dusty year. When the world was locked deep in ice, it was also dry and windy and bare. Vast plains lay exposed where there are now forests and seas, and the winds scoured those bare lands and lifted fine dust high into the air and carried it for thousands of kilometers and some of it settled faintly onto the Greenland snow. So a cold layer is a dirtier layer. If you measure the dust trapped in the ice, the cold years are grimy with it, and a warm year is a cleaner year. When the world warmed, the dry plains greened and grew quiet under vegetation, the winds calmed, the dust fell away. So as the climate flipped from cold to warm, the dust in the ice could drop dramatically. By something like a factor of 10, an entire order of magnitude, within just a few years. Imagine that. The very same handful of years in which the oxygen says the air leapt warmer, the dust says the wind died down and the world stopped being a desert and started somehow to soften. And there is a third voice in the layer, fainter still but there. The ice traps tiny bubbles of ancient air, actual, literal air, the very atmosphere that surrounded that long-ago snow, sealed inside as the snow compressed into ice. And in those bubbles you can measure methane, a gas that the living, breathing, wet parts of the world give off. The marshes, the wetlands, the warm, rotting abundance of a living landscape. When the world was cold and dry, there were fewer wetlands, less life seeping that gas into the air, and the methane in the bubbles is low. When the world warmed and grew wet and green, the wetlands spread, the world exhaled more, and the methane rose. So picture all three of these messages now, lying together in the same set of layers. The oxygen, saying the air warmed. The dust, saying the winds calmed and the deserts greened. The methane, saying the wet, living, breathing world came rushing back. Three separate witnesses who never spoke to one another, all describing the same astonishing event in the same handful of years. Cold, dusty, dry, low in methane, and then, suddenly, in a single, short stretch of layers, warm, clean, wet, alive. That is what an abrupt climate flip looks like, written 4 ways at once, in a column of ice no thicker than your arm. And now we can finally give these flips their name and meet the 2 men who first truly understood them, and tell the whole long story properly, the way it deserves to be told, slowly, in the dark. They are called Dansgaard Oeschger events, and they are named for 2 people, Willi Dansgaard, a Dane, and Hans Oeschger, a Swiss. 2 careful, patient pioneers who, more than perhaps anyone, taught the world how to read the message in the oxygen. Dansgaard, especially, who saw early on that the heavy and light oxygen in old ice could be turned into a thermometer of the past, and Oeschger, who brought his own deep skill in reading the trapped breath of the ancient atmosphere. Between them, and the many who worked alongside and after them, they took those faint, frozen signatures and turned them into a story of the planet that nobody before had been able to tell. And the story the ice told them was this. During the last great glacial period, that long stretch of deep cold that gripped the Earth for tens of thousands of years before our own warm age, the climate of the North Atlantic did not simply sit there, frozen and unchanging, waiting patiently for the ice age to end. It jumped again and again and again, roughly 25 times the cold glacial world of the north suddenly warmed by that astonishing 8 to 16 degrees Celsius within decades, and in some cases the steepest of them perhaps within a single decade. And then, having leapt up so violently, it would slowly, gently slide back down again into the cold over centuries, sometimes over thousands of years. I want you to picture the shape of that, because the shape is the whole secret, and it is a shape you can almost feel with your hand in the dark. Imagine drawing it. The line shoots up. Steep, sudden, almost a cliff. That is the warming. Decades. A human lifetime or less. And then from the top, the line eases back down, slowly, unhurried, a long, gentle slope. Centuries of cooling, like a tired wave drawing back from a beach. Up like a cliff, down like a hill. Up fast, down slow. Over and over 25 times, all the way through the long ice age. Scientists call that shape a sawtooth, a row of those steep up, slow down teeth marching across the ice record. And that sawtooth is the fingerprint. It is the diagnostic signature, the thing that tells you this was no gradual drift, no slow 10,000-year thaw. This was the climate of a hemisphere snapping abruptly into a warmer state and then sighing slowly back down again in a rhythm the planet repeated some 24 times. These warm phases, the tops of the teeth, have a name of their own. They are called interstadials, the warm windows that opened in the middle of the cold, and the long, cold troughs in between are the stadials. Don't worry about holding the words, just hold the picture. Cold trough, sudden warm window, slow slide back to cold trough and another sudden warm window. The world, through the long ice age, breathing, not evenly, not gently, but in great sudden gasps of warmth, followed by long quiet sinkings back into cold. And we have counted them, these gasps, and numbered them. The youngest, the most recent of the great warm jumps, is called DO1, and it happened around 14,700 years ago. Recent enough, almost, that you can feel the human nearness of it, near the very end of the Ice Age. And from there the count runs backwards, deeper and deeper into the ice and into time, DU2, DU3 and on, all the way back to DU25, which lies roughly 115,000 years ago near the very beginning of that last glacial world. 25 numbered teeth on the saw, 25 times the north flipped warm and then cooled back. A long, slow heartbeat of abrupt change recorded in the cores that Dansgaard and Oeschger and those who followed them lifted out of Greenland. Cores with names like GRIP and GISP2 and NGRIP, names that sound like quiet machinery, but are really just the names of the holes we drilled, the deep, clean wells we sank into the ice to bring the diary up into the light. And here, I think, is where the wonder of it sharpens into something almost dizzying, if you let yourself follow it slowly. Because when the world flipped into one of those warm interstadials, it didn't only get warmer. Everything changed at once, and fast. The snow itself fell differently. As the warm window opened, the amount of snow piling onto Greenland each year could double, simply double, because warmer air carries more moisture, and a warmer, wetter north dropped far more snow. So a researcher counting layers can actually see the years grow fatter as they cross the threshold into a warm phase, the band swelling as the climate flips. And the dust, as we said, could drop tenfold in just a few years. And the methane rose, all of it, together, within the span of a few short layers, within, in the steepest cases, the lifetime of a single person who happened to be alive at exactly the right and remarkable moment in the deep past. Try for just a moment to stand inside one of those moments, not to fear it. There is nothing to fear. It ended long, long before any of us, and our own ancestors, our actual human ancestors, lived through several of these and walked out the other side. Just to picture it. A person somewhere in the north of the world more than 14,000 years ago. A person who began their life in a cold, dry, wind-swept world, a world of dust and hard winters and a thin, mean kind of weather, and who, simply by living a normal length of life, by growing old in the ordinary way, watched that world warm around them by something approaching 16 degrees, watched the winds calm, watched the dust settle and the land begin here and there to soften and green. A whole different climate arriving inside one life, the grandparents born into one world, the grandchildren growing up in another, and no one among them with any way of knowing what we now know, that the very snow falling on the distant ice was quietly writing all of it down, layer by layer, to be read by strangers an age later in a small white room with a careful finger resting on a single band. And this is the question that the ice leaves hanging in the cold air, the question that Dansgaard and Oeschger and everyone since has circled and not entirely answered, and it is the question I want to leave gently open as we drift on. What, in all the wide machinery of the planet, could possibly flip an entire hemisphere that fast? What could take a whole frozen ocean and a whole frozen sky and tip them in a single decade into a warmer state, and then, just as strangely, let them sink slowly back? A glacier moves slowly. A continent moves slowly. The great rhythms of the Earth, the ones we are taught about, the wobbles of the planet and the slow march of the seasons across the ages, those grind along over tens of thousands of years. They do not snap. They do not leap. So what does? The answer, as far as we can tell, and it is the leading explanation, worked on still, refined still, debated still in its details, has to do with two things you cannot see written directly in the ice, but which the ice points to like a finger pointing at the dark. One is the sea ice, the floating skin of frozen ocean that spreads across the cold North Atlantic and pulls back when things warm. And the other is something larger, deeper, slower, a vast circulation of water in the Atlantic that carries warmth from the south up into the north. A great, quiet, turning current of the sea with a name we will come to that can strengthen and can weaken. And when it shifts the warmth of half a hemisphere with it. When the cold skin of sea ice pulls back from the North Atlantic, the ocean beneath, holding its stored warmth, can suddenly breathe that heat straight up into the air above, and the air over the north can warm, faster than anything on land could ever manage. And that, the rapid retreat of sea ice and the sudden release of the ocean's hidden warmth, coupled to the strengthening and weakening of that great turning current beneath, may be the engine, or much of the engine, behind the steep cliff of every warming tooth in that long saw-toothed saw. But hold that lightly for now. We will come back to the current and to the ice and to a strange and beautiful idea about how the two ends of the Earth might rock against each other like a balance beam. For now, it is enough to know that the question is real, and that the answer hides in the sea, in moving water and floating ice, and that we are going to walk down to the water's edge together, slowly, in just a little while. Because there is more in the ice than the warm jumps. There is the matter of what came surging out of the cold the other way, out of the land and into the sea, in great drifting fleets of broken ice, 6 separate times, scattering stones across the floor of the deep Atlantic that you could, even now, hold in the palm of your hand. There is a man named Hartmut Heinrich, and what he found in the year 1988, lying quietly in the mud at the bottom of the ocean. But that is the next stretch of our descent, and we have come a long way already, down through the layers, down past the oxygen and the dust and the trapped breath of ancient air, down to the very edge of the great turning sea. So let your hand rest for now on that single band of ice, the one holding a decade in which a whole world reorganized itself. And let us pause here a moment, in the cold quiet, before we go on down. Let your hand stay there a moment longer, on that band no thicker than your finger, and consider what you are really touching. You are touching a single year, just one. The way a tree sawn through shows you its years as rings, a fat, pale ring for the wet season, a thin, dark line for the lean one, The ice keeps its own count, layer on layer, each winter's snow pressed down upon the last, season folding into season, until a whole age of the world is stacked beneath the drill like the pages of a book no one wrote and everyone can read. And the people who learned to read it counted those layers the way you might count rings, one by one, down from the top, where the years are still loose and distinct, where you can lay a finger between this winter and that one and say, here, this is where one year ended and the next began. Near the surface, the counting is easy and sure. Deeper down, where the weight of all that ice has squeezed the layers thin as paper, the reading grows harder and the counters lean on other signs to keep their place. For the ice does not only remember warmth and cold, it remembers the weather of the whole world, caught and held in the falling snow. When the air over the great northern lands was cold, it was also dry and dusty, and the wind carried grit from far-off deserts and dried-up plains and laid it down in the snow so that a cold year arrives in the core as a dirty year, thick with dust. And when the warmth came, the dust thinned away almost to nothing, the world grew wetter, the marshes breathed, and the very air held more of that faint swamp gas, methane, which the snow caught and sealed in tiny bubbles as it fell, cold and dusty and quiet, warm and wet and breathing. 3 signals laid down together in the same falling snow, agreeing with one another, telling the same slow story 3 different ways. But the thermometer itself, the real thermometer, frozen into the layer, is something stranger and finer than dust or gas. It is hidden in the water itself, in the very oxygen of the ice. For oxygen comes in more than one weight. Most of it is light, but a small share is a little heavier, and when water evaporates from the warm sea and travels north as cloud and falls at last as snow upon Greenland, the balance between the light oxygen and the heavy oxygen shifts ever so slightly with the temperature of the air. Colder air and the heavy kind grows rarer in the snow that falls. Warmer air and a touch more of it survives the journey north. So in the ratio between the two, in that quiet measure the readers call delta O18, written as a small Greek letter and a number, D18O, there sits a thermometer, frozen at the instant the snow came down, holding the temperature of a single ancient winter, the way amber holds a fly. Lower the ratio and the air was colder when that snow fell. Raise it and the air was warmer. And so a researcher, standing in a cold white room with a column of Greenland ice laid out before them, can move a finger slowly down the layers and watch the temperature of the deep past rise and fall beneath their hand, year upon year upon year, like reading a fever chart of the whole northern sky. 2 men, more than any others, taught us to read it. A Dane named Willi Dansgaard and a Swiss named Hans Oeschger. They were among the first to understand that the oxygen locked in the snow was a thermometer, that the ice was not a frozen blank, but a frozen record, patient and exact. And when they, and those who followed them, counted their way down through the great Greenland cores, through the one called GRIP, and the one called GISP-2, and the deeper, finer one called NGRIP, what they found in the delta O18 was not a smooth and gentle slide from cold to warm and back. It was a saw, a long row of teeth climbing the wall of time. For during the last long ice age, that vast cold stretch before our own warm and gentle days, the record does not drift, it jumps. Some 25 separate times, the North flung itself out of the cold and into a sudden warmth, the air over Greenland leaping upward by as much as 8 degrees, 10 degrees, in places 16 degrees, and not over the slow grind of ages, but within decades. In some of those jumps, perhaps within a single 10 years, perhaps within the span of one child's growing up. These are the Dansgaard-Oeschger events named for those two careful men, and they are the warm jumps, the rising teeth of the saw. And every tooth has the same strange shape. The warming is a cliff, steep, sudden, almost vertical in the record, the whole climate hauling itself upward in a human lifetime or less. And then, having climbed, it cools again, but slowly now, gently, over centuries and sometimes thousands of years, sliding back down the long, gradual slope toward the cold until the next sudden cliff flings it up again. Steep up, slow down, steep up, slow down. A sawtooth, repeated across 100,000 years, each tooth a flip and a falling away, each one a world reorganizing itself and then settling, with infinite patience, back toward the ice. The readers gave them numbers, counting backward from the youngest. The most recent great jump, DO1, lies about 14,700 years back, near the very end of the Ice Age, almost within reach of the warm world we know. And the count runs back from there, tooth by tooth, deeper and older, down through the layers, all the way to DO25, some 115,000 years ago, near the far beginning of that long glacial night. 25 times the North warmed in a lifetime. 25 times it cooled again at leisure. And the jumps left more than a mark on the thermometer. When one of these warmings arrived, the very snowfall over Greenland could double, near enough, almost overnight, in the slow reckoning of the ice. The dry, starved, dusty world suddenly turning wet and generous, laying down twice the snow, while the dust that had thickened every cold layer dropped away to a tenth of what it was, clearing within a few years as if a window had been wiped clean. A whole northern climate, its winds and its waters and its weather, swinging from one state to another in less time than it takes a person to grow grey. And here is where the wonder turns sharp, and a question opens beneath us like a dark shaft in the ice. What could possibly do that? What could take an entire hemisphere? Its seas, its skies, its winds, running the whole way round the pole, and flip it, in 10 years, from bitter cold to something nearly mild, and then, ages later, do it all again? Not the slow tilt of the Earth toward the sun, which moves far too gently for this. Something faster. Something that can change its mind in a decade. And the answer the readers keep returning to lies down at the water, in the floating sea ice that comes and goes upon the northern ocean, and in that great turning current beneath it, the one we have left waiting. The current we left waiting is not a simple thing. It has been drawn, in the diagrams you might find in a classroom, as a single great loop. A tidy blue arrow diving cold and salty into the depths of the North Atlantic, a red arrow riding warm and shallow back across the surface toward Europe, the whole business turning like a wheel in a mill. It is a useful picture. It is also, in the way of all useful pictures, incomplete in ways that matter. The real system, or what oceanographers call the Atlantic Meridional Overturning Circulation, or AMOC, is something messier and stranger, and, in its strangeness, more interesting. A whole family of interlocking motions spread across the breadth of an ocean, not a single pipe but a vast, slow breathing of the sea, drawing heat northward, sinking cold and salty water into the deep, and releasing its warmth to the air above. The mechanism is genuine, the simplicity is the fiction, and it is this system that lies at the heart of the next chapter in our reading of the ice. Because while Willi Dansgaard and Hans Oeschger were working outward from their ice cores, learning to hear the rapid heartbeat of the warm jumps, something else was being found entirely, not in ice at all, but in the mud of the deep Atlantic floor. and the person who found it was a German marine geologist named Hartmut Heinrich, working in the late 1980s, pulling up sediment cores from the bed of an ocean that had been, in its slow way, keeping its own diary. The year was 1988. Heinrich had been studying the layers of sediment that had settled over tens of thousands of years onto the floor of the North Atlantic. Sediment cores are long, narrow cylinders of this accumulated material. Mud and fine particles and the shells of tiny creatures, pulled up from the deep by a weighted tube, lowered on a cable, a kind of slow, blind fishing in enormous depths. The layers within these cores are red, like the ice layers are red, from top to bottom, youngest to oldest, each band representing a span of time, a season, or a decade, or a century, compressed into a centimetre or a few millimetres of seafloor. And within these cores, Heinrich saw something that did not belong. At several distinct levels, layers that could be dated by their position in the record, cross-checked against other cores from different locations, there appeared bands of coarse material. Sand, grit, small pebbles, fragments of rock that had no business being in the middle of a deep ocean. The fine-grained sediment that settles slowly through thousands of meters of water could carry no such thing. Clay travels that way, and the microscopic skeletons of plankton, but pebbles do not rain down through open ocean on their own. There is only one mechanism that can carry a rock the size of your thumbnail 1,000 kilometers out to sea and then release it to fall to the bottom. That mechanism is ice. Specifically, it is a glacier, or a fragment of one, an iceberg, broken off from a continental ice sheet at the coast, drifting outward on the currents, carrying frozen inside it the debris that had been ground up by the glacier as it moved slowly over bedrock for centuries. As long as the iceberg floats, the rock floats with it. And when the iceberg melts far from land in the middle of the ocean, the rock falls. Straight down through kilometers of dark water, down to the floor, where it settles into the mud and stays. The word for these fallen fragments is drop stones, and you could, if you were given one, hold it in your palm. It is a real object, a piece of Canada. From the grinding heart of the Laurentide ice sheet, the enormous frozen mass that covered most of the continent above the Ice Age, carried outward in the belly of an iceberg, released somewhere over deep Atlantic water, and then lying in the dark of the ocean floor for 12,000 years or 20,000 years, waiting for Hartmut Heinrich and his coring tube to find it. What Heinrich recognized, looking at the layers in his cores, was that these debris bands did not appear randomly. They appeared in clusters at specific moments in time, separated by long intervals of ordinary fine-grained settling. And they appeared, this was the crucial thing, across many cores from many different locations spread across the North Atlantic, all at the same times. The coarse debris was not a local accident, a single stray iceberg carving from a small glacier and drifting a little ways to sea. It was an event. Something large had happened multiple times at the scale of an ocean. What he was looking at was the evidence of armadas. Not one iceberg, but armies of them. Fleets vast enough that the material they dropped, melting as they drifted, carpeted the seafloor across hundreds of thousands of square kilometers with a recognizable band of debris. The events that carry his name, Heinrich events, are defined precisely by these layers. The Heinrich layers, or more formally, the ice-rafted debris layers, often abbreviated to IRD. When you hear those three letters in a discussion of past climate, you are hearing the fingerprint of one of the great convulsions that the last ice age delivered repeatedly to the North Atlantic. There are 6 such layers clearly identified in the record. 6 armadas. 6 separate moments when the North Atlantic received from the north and west an outpouring of ice on a scale that is difficult to hold in the mind. The source of the ice in each case can be traced. The rock in the debris layers carries a geological signature, the mineral composition of the pebbles, the specific types of crystals within them, that matches the geology of a particular part of North America. The provenance points, again and again, to the Hudson Strait region of Canada, the narrow channel of water between Quebec and Baffin Island, through which Hudson Bay opens to the Labrador Sea. The ice was coming from there. From the enormous dome of the Laurentide ice sheet, pressing outward under its own incomprehensible weight, pushing tongues of ice down through that strait and into the open ocean, where they carved into icebergs by the countless thousands and were carried eastward by the currents. Why it did this 6 times and not continuously and not more or fewer times, that is a question the ice and the sediment can suggest answers to, but cannot answer cleanly. The ice sheet was not simply spilling over at the edges the way a glass overflows. Something about the internal dynamics of the glacier itself, the way enormous ice sheets can become unstable from their own pressure and their own internal warmth at the base where the ice meets the rock, is thought to have contributed. Ice that gets thick enough begins to slide faster. Sliding ice produces heat. Heat produces meltwater at the base. Meltwater lubricates the sliding further. The system can accelerate catastrophically and suddenly, discharging enormous volumes of ice into the sea before the sheet thins enough to slow itself down. The events recur not because something external switches them on each time, but because the ice sheet builds, destabilizes, purges, rebuilds, and destabilizes again on its own slow and terrible schedule. And the timing of these purges, as read from the sediment record and cross-referenced against the ice cores from Greenland, was not random in another sense. The Heinrich events fall at specific moments within the larger cycle of the Dansgaard Oeschger pattern. They fall at the coldest points, at the lowest troughs of the long, slow, cooling limbs, the coldest reaches of what the researchers call the stadials, the cold intervals between the warm interstadials. The Heinrich events are, in this sense, stadials within stadials, the coldest moment of an already cold phase, as if the planet, in its most frigid condition, reached a point of instability that the ice sheet could no longer hold. And when those armadas finally surged out and melted, the ocean received them, received the cold, and received something else that mattered even more to the circulation that drives the climate of the whole northern hemisphere: fresh water. Here is the mechanism described as simply as the truth allows. The North Atlantic is salt water. It is, in parts, among the saltiest stretches of open ocean on Earth. That saltiness matters to the overturning circulation because salt makes water denser, and dense water sinks. In the northern reaches of the Atlantic, near Iceland and Norway, and the Labrador Sea, the surface water has been chilled by the Arctic air above it, and is already dense for that reason, and the additional density from the salt makes it sink deeply to the floor of the ocean, where it moves slowly southward as a cold river at the bottom of the sea. As it sinks, it drags more warm surface water northward behind it to replace what has gone down. This is the pump at the heart of the overturning circulation. Without it, the warm flow northward slows. Now pour fresh water on top. Fresh water is lighter than salt water. It floats. A fresh water cap on the North Atlantic surface does not mix easily downward. It sits on top of the salty water and prevents it from cooling enough to sink, because cooling a floating freshwater layer does not produce water that is denser than the salt water below. The pump loses its head of pressure. The sinking slows. The warm surface flow from the south weakens in response because it is the sinking in the north that drives the drawing in of warm water from below. And as the warm flow weakens, the heat it delivers to the North Atlantic and the surrounding continents diminishes. The climate of the North Atlantic region cools. This is the mechanism the Heinrich armadas are thought to have triggered. The meltwater from millions upon millions of icebergs dissolving into the surface of the North Atlantic over spans of centuries or perhaps shorter, freshening the ocean surface enough to slow the overturning circulation, to reduce the northward delivery of heat, and to intensify and prolong the cold that was already there. It is a feedback loop expressed in salt water and ice. The icebergs chill the ocean directly with their own cold mass, and indirectly by muffling the pump that was keeping the region from being colder still. And the sediment cores show that these events had reach. The signature of the Heinrich layers, the coarse debris, the changed chemistry of the ocean surface, appears from the waters off Portugal in the east to the margins of the Laurentide continent in the west. The cold that followed the armadas was not a regional footnote. It was a reorganization of the Northern Ocean on the scale that the ocean is capable of, which is to say, on the scale of an entire hemisphere's thermal budget. It was, in its way, the largest expression of what the Dansgaard Oeschger record describes. The Dio warmings were jumps, steep and astonishing. The Heinrich events were the counterforce, the deep stalls, the cold intensified beyond the ordinary glacial cold by the meltwater cap and the weakened circulation. Between the two poles of that system, the rapid warm jumps of the Dio interstadials on one side and the slow freezing intensified by the iceberg armadas on the other, the last ice age took its shape. And here, with the machinery of the North Atlantic laid out before us, the sinking of salt water, the northward flow of warmth, the vulnerability of the whole system to fresh water, here is the moment to introduce a third actor in this story, one that has been waiting behind the curtain since we first placed our finger on that Greenland ice layer. Antarctica. The South Pole has its own cores, long, patient, drilled in the silence of a continent no one has ever lived on, pulled up from ice that accumulated over hundreds of thousands of years in the driest, coldest, most remote place on the surface of the Earth. The core from Vostok station, drilled by a Soviet and later Russian operation that began in the 1970s, extends through ice more than 3 kilometers deep and reaches back past 400,000 years. The core from the EPICA Dome C site, the European project for ice coring in Antarctica, goes even further, past 800,000 years, the longest continuous climate record yet extracted from the planet's own frozen archive. These southern cores carry their own oxygen-isotope record, their own version of the D18O thermometer frozen in each layer. And when researchers compared the southern temperature signal, as read from these cores, with the northern signal read from GISP2 and GRIP and NGRIP in Greenland, they found something that was, on first encounter, deeply strange. The two poles were not doing the same thing at the same time. They were, in a particular and repeating way, doing opposite things. When Greenland warmed suddenly into a Dansgaard Oeschger interstadial, when the northern record showed one of its sharp, steep jumps, the Antarctic record showed, at roughly the same moment in deep time, a slight slowing of its own warming, or even a modest reversal. And when the North Atlantic cooled, when a Heinrich event deepened the cold in the north, the south continued to warm, or warmed more quickly. The two hemispheres were rocking against each other. When one rose, the other fell. Not perfectly, not with mechanical precision, but enough that the pattern repeated through the ice ages, clearly enough that it could not be coincidence. The name given to this phenomenon is the bipolar seesaw. Imagine a balance beam, the kind you might picture balanced on a fulcrum at its center, a long plank tipping left and then right, and then left again. The two ends of the beam are the two poles of the Earth. When the north end dips cold, the south end rises warm. When the north end rises toward warmth, the south end yields. The planet, in a sense, cannot warm everywhere at once during these events because The mechanism that does the redistributing is the Atlantic circulation itself. The explanation offered by researchers and supported by both the data and by modeling work runs as follows. When the Atlantic overturning circulation is strong, it actively pumps heat northward across the equator from south to north. It is taking warmth out of the South Atlantic and delivering it to the north. The north benefits. But that northward transport comes at a cost to the south. It is drawing heat away, and the south, left with less of the warmth the ocean would otherwise retain or redistribute, cools slightly or warms more slowly than it otherwise would. Now, slow the circulation as happens during a Heinrich event when fresh water caps the sinking regions in the north. The northward pumping of heat weakens. Less warmth is extracted from the South Atlantic. The south is no longer being drained of its heat at the same rate, and so, as the north suffers under the weakened delivery of warmth, the south accumulates the heat that is no longer being taken from it. The south warms, or more precisely, the south stops being cooled to the same degree that the strong circulation imposes. The seesaw tips. This is not a metaphor exactly. It is a description of thermodynamics operating over a hemisphere through the medium of an ocean. The Atlantic, in this picture, is not merely a body of water between continents. It is a heat engine, and like all engines, it can be in different gears, running fast and distributing warmth widely to the north, or running slow and allowing the south to hold what it has. The gear is set in part by how much fresh or cold water arrives at the sinking regions in the north, and the bipolar seesaw matters to this account of the 6 flips, because it is not merely an interesting curiosity about the ice ages, it is the connective tissue of the whole story. It ties together the Dansgaard Oeschger warm jumps in Greenland, the Heinrich armadas in the North Atlantic sediments, and the slow counter-warming in the south into a single, coherent system. They are not separate mysteries happening to occur in the same period of time. They are aspects of the same machinery, the same great thermal engine of the ocean, expressing itself differently at different latitudes depending on which phase the circulation has settled into. When the circulation is vigorous, Greenland warms. When the circulation falters, suppressed by fresh water, whether from the Heinrich armadas or from other meltwater pulses, Greenland cools, the DO interstadial ends, and the south slowly accumulates the heat that is no longer being sent away. This is why the DO sawtooth in Greenland and the longer, smoother, warming and cooling cycles in Antarctica look like imperfect mirror images of each other. They are the two ends of the same beam. But the seesaw is not simple, and it is important to say this clearly. The word seesaw suggests perfect alternation, a tidy back and forth. The reality is something blurrier and richer. The timing offsets between north and south vary from event to event, measured in decades to centuries, and the amplitude of the southern response depends on how large and how sustained the northern perturbation was. The mechanism is broadly understood, broadly supported by the evidence from the cause, but its precise workings, the exact pathways through which the ocean communicates between hemispheres, the role of the winds and the sea, ice in the south in mediating the signal, remain an active area of research. Oceanographers and paleoclimatologists are still working out the detailed plumbing. The seesaw itself is not in doubt. Its inner architecture still holds secrets. We will return to the south to its own great reversal in its own time. But first there is a smaller, and in some ways more unsettling chapter to read from the ice, because the events we have described so far all took place during the last ice age, when the world was in its deeply different glacial state. Vast ice sheets over North America and northern Europe, sea level 100 meters below where it stands today, a world so unlike our own that the strangeness is almost impossible to hold in the imagination. The next flip happened after all of that had ended. It happened inside our own age, inside the warm interglacial that we are still living in, the Holocene, in a world that was recognizably closer to the one we inhabit. And it is in many ways the most quietly disturbing entry in the ice record, because it tells us that the stable world we assume we live in is not as stable as it sometimes seems. That story belongs to the next movement of our descent. But before we arrive there, let the image settle for a moment. A pebble on the floor of the Atlantic. Not a metaphor, not a number on a graph. A real piece of rock, perhaps the size of a walnut, worn smooth by the grinding of glacial ice over bedrock, carried eastward across an ocean in the frozen belly of an iceberg the size of a building, released in the dark of deep water when the ice finally surrendered to the warmth of the sea and falling slowly, slowly, through kilometres of cold and pressure to land without sound on the mud of the ocean floor. And then nothing. Stillness. The quiet sedimentation of centuries, one thin layer settling over another, covering the pebble, sealing it in. And 12,000 years later, or 15,000, a steel coring tube descends from a research vessel somewhere in the North Atlantic, pushes through the mud, and finds it. That is the scale of what Hartmut Heinrich was reading. Not a model, not a simulation, the rock itself. And there were 6 armadas that left such rocks, 6 surges from the Laurentide, 6 freshwater pulses to the North Atlantic, 6 deepenings of an already deep cold, 6 moments when the overturning circulation was pushed back, and the North was left without the warmth the ocean had been sending it. 6 entries in the sediment diary of an ocean that was recording everything, patiently, in a language of pebbles and clay. Between those 6 great stalls, the Dansgaard Oeschger warmings arrived and receded. The ice over Greenland wrote its oxygen-isotope record. The dust came and went, the snow accumulated in thin annual layers, each one a year, countable, readable, a diary written in ice one winter at a time. The whole vast archive of the last glacial period, from roughly 100,000 years ago to roughly 12,000 years ago, is there in those cores, in those sediments, patient and complete in ways no human record can approach. And all through that archive, the seesaw between the poles was rocking, quietly, through its long, slow rhythm. The north cooling while the south warmed, the north warming while the south eased back. The Atlantic circulation running fast and running slow, distributing the heat of the planet according to its own deep logic, a logic written not in the language of diplomacy or economics, but in the language of salt and freshwater and the density of seawater and the direction of the wind. What we carry forward from this into the next chapter of the ice record is this understanding, that the climate system has a particular kind of vulnerability. It is not a simple, linear machine that warms gradually when it receives more energy and cools gradually when it receives less. It is a system with distinct states, states that can be stable for long periods and then shift rapidly from one to another when a threshold is crossed. When enough fresh water arrives in the wrong place, when enough sea ice retreats or expands, when the circulation tips from one mode to another. The shift can be sudden. The recovery, or the next shift, may take centuries, or it may take a decade. The Dansgaard Oeschger events showed us the sudden warming side of that shift. The Heinrich events showed us the sudden deepening of cold, the armadas and the meltwater, and the stalled circulation. The bipolar seesaw showed us that these were not isolated regional events, but the expressions of a planetary thermal engine redistributing its warmth between hemispheres. And what comes next in our descent shows us that none of this was limited to the ice ages, that the system we have described in all its threshold-crossing instability was capable of one more convulsion even after the ice had retreated, even after the world had warmed back into something resembling our own climate, even inside the very interglacial that holds us now. The warmth that followed the Ice Age did not arrive cleanly without stumble. It arrived in stages with reversals, with cold relapses that lasted long enough to reshape the world. And one of those reversals, and one of the most clearly recorded, most precisely dated, occurred not 12,000 years ago or 20,000 years ago, but 8,200 years ago in a world that was already broadly warm, already greening, already beginning in parts to see the first tentative experiments of human settlement and cultivation. A world, in other words, that looked enough like ours to carry a particular kind of weight. But before we arrive at that cold morning 8,000 years ago, before we read that chapter in the ice, we should understand the shape of what the record shows in the transition out of the Ice Age, because the 8.2 kilo-year event does not arrive without context. It arrives at the end of a long, complicated deglaciation, a warming that had been underway for millennia, but that was itself interrupted repeatedly by the machinery we have just described. The deglaciation of the last Ice Age was not a smooth, gradual warming. Nothing about the climate of this period was smooth. The great ice sheets that had covered North America and northern Europe were retreating, losing mass to a warmer ocean and a warmer sky, but they were retreating unevenly in fits and starts. Meltwater was flowing from their margins and into rivers and lakes and eventually to the sea, and that meltwater was, as we now understand, capable of interfering with the Atlantic circulation in exactly the way the Heinrich armadas had. The same mechanism, the freshwater cap, the slowed sinking, the weakened northward heat transport, was available to operate not just during the glacial period, but during the deglaciation itself. And operate it did. The world was warming broadly, and within that broad warming it stumbled repeatedly. The ice will tell us how. The most dramatic stumble of all in our current warm world arrived without any of the glacial machinery that had driven the earlier flips. No iceberg armadas, no stadials within stadials, no descent into the deep cold of a full glacial period. What arrived was something quieter in its cause and more surprising in its timing. A cold snap that settled over the North Atlantic region and the lands around it at a moment when, by every reasonable expectation, the hard work of warming was essentially done. 8,200 years ago, give or take a century in either direction depending on which archive you consult, which core you read, which cave in which limestone hill preserves the thinnest and most precisely dated layer. But the signal itself is not in doubt. It is there in the Greenland ice, a dip in the oxygen-isotope ratio that sits in the column like a held breath. It is there in European cave stalagmites, those slow stone columns that grow from the floor of a cave as mineral-rich water drips from the ceiling, year after patient year, each drop leaving a fraction of a millimeter of calcite, each layer preserving the chemistry of the rainwater that fed it. It is there in lake sediments across northern Europe, in the pollen records preserved in bogs, in the patterns of vegetation that abruptly shifted for a century, and then, as quietly as it had come, shifted back. The 8.2 kilo-year event, as it has come to be known in the scientific literature, is not the largest climate event of the last 100,000 years. That distinction belongs, by some distance, to the great Dansgaard Oeschger warmings and the Heinrich cold pulses that dominated the glacial period. Nor is it quite as dramatic in raw temperature terms as the younger Dryas, that long cold interruption that had ended only about 3,000 years before the 8.2 kilo-year event struck. But the 8.2 kilo-year event carries a different kind of significance, one that becomes clear the moment you understand its context, because this cold snap did not arrive in a glacial world, it arrived in our world. In the warm interglacial, the Holocene, the unusually stable chapter of climate history within which all of human civilization has unfolded. And it arrived while the world was already broadly warm. That is the detail that changes everything. It means the warm world, the stable, gentle, interglacial world, is not immune. It means the machinery that had driven those wild oscillations of the glacial period, the meltwater pulses, the freshwater caps, the slowed Atlantic circulation, did not simply switch off when the Ice Age ended. It lingered. It retained the capacity for some centuries yet to reach into the warming world and pull it briefly backward. The 2-kilo-year event is in this sense the clearest demonstration in the entire ice record that even interglacials can lurch. That even in the chapter where we live, the ground beneath us is not entirely still. To understand what caused it, you need to picture something that no longer exists, something that existed 8,000 years ago across a vast stretch of what is now central Canada, and that was, in its day, the largest body of fresh water on the surface of the Earth, larger than any lake that exists today, larger than the Caspian Sea, larger than any of the Great Lakes, larger in fact than all of the present-day Great Lakes combined, and then some. It had no single name at the time because there were no people with written languages to name it, but the geologists and paleoclimatologists who have reconstructed its history have given it names after the fact. We call parts of it Lake Agassiz and Lake Ojibwe. It is easier, though, to simply hold in mind the scale of the thing, a shallow, enormous inland sea of glacial meltwater held in place not by solid bedrock walls, but by the ice itself, by the southern and eastern lobes of the decaying Laurentide ice sheet, which still sat across the northern margin of the continent, even as the warmer conditions of the early Holocene were eating steadily at its edges. Imagine then a dam made of ice. Not a narrow dam, but a broad, irregular, shifting margin of glacial ice that happened to stand between this enormous lake and the sea. Meltwater had been collecting behind this dam for thousands of years, fed by the runoff from the retreating ice, growing deeper and wider as the ice walls that contained it thinned and shrank. The water had nowhere else to go, it was trapped. And all the while, the ice dam was getting weaker. You may have seen, perhaps in a television program about glaciers or in a film set in the high mountains, the phenomenon of a glacial lake outburst flood, a jökulhlaup, as the Icelandic word has it. A pocket of meltwater trapped behind or beneath a glacier accumulates until the pressure it exerts against the ice exceeds the strength of the ice dam. And then it goes. Not slowly, not in a trickle. It goes in a torrent that can last hours or days and can carry volumes of water that dwarf anything a river in ordinary times could manage. The same physics, scaled up by a factor that is almost impossible to hold in the mind at once, is what appears to have happened to Lake Agassiz and Lake Ojibwe roughly 800 years ago. The trigger was the final weakening and failure of the ice dam along what is now the Hudson Strait, the narrow channel between the northeastern coast of Canada and the southern tip of Baffin Island that connects Hudson Bay to the Labrador Sea. As the Laurentide ice sheet continued its retreat, the ice dam that had been holding these lakes back gave way. And when it gave way, the water moved. The estimates of how much water and how quickly are themselves remarkable enough to sit with for a moment. Something on the order of 100,000 cubic kilometres of fresh water. 100,000. To give that number a shape, it is roughly enough water to fill the present-day Hudson Bay several times over, or to raise the global sea level by perhaps 1 to 2 meters in a relatively short time. And the evidence suggests that a very large fraction of this volume was released not over centuries, but possibly within a period of years, perhaps even within a single year, or a few years at most. A flood of glacial meltwater, cold and fresh and enormous, pouring through Hudson Strait and out into the Labrador Sea, and the North Atlantic. And here the mechanism is the same one that has appeared throughout this story, because the same mechanism was available and the same vulnerability was present. Fresh water is lighter than salt water. It does not sink. And in the North Atlantic, the sinking of cold, salty water at high latitudes is not merely a feature of the ocean. It is the engine of the Atlantic meridional overturning circulation, the great slow pump that moves tropical warmth northward and keeps the regions around the North Atlantic warmer than their latitudes alone would suggest. A sudden, massive influx of fresh water at the surface of the North Atlantic puts a lid on that ocean, a lid of buoyant fresh water that the heavier salt water beneath cannot easily penetrate. The sinking slows. The pump weakens. The northward transport of warmth is interrupted, and the North Atlantic region grows colder. This is what the ice records. A sharp, clear dip in the D18O ratio in the Greenland cores, a signal that says the air over Greenland was colder for a period than it had been in the centuries before. The reconstructed temperature depression varies somewhat depending on the archive and the method, but the estimates center somewhere in the range of 1 to 3 degrees Celsius of cooling averaged across the broader North Atlantic region, with larger local anomalies over Greenland itself. 1 to 3 degrees sounds modest in a way. It is not the 16 degrees of a Dansgaard Oeschger warming, but it came from a world that was already warm, and it was sharp enough and sustained enough, persisting for perhaps 150 years, give or take, to leave its fingerprint not just in the ice of Greenland, but in the rocks of European caves and in the mud at the bottom of European lakes. The stalagmites are worth dwelling on for a moment, because they are a different kind of memory than the ice. A stalagmite grows in the dark, in the silence of a cave, as water drips from the ceiling and deposits its dissolved minerals one thin layer at a time. The chemistry of that calcite depends on the chemistry of the rainwater that percolated down through the soil and rock above. And the chemistry of rainwater depends, in a complicated but decipherable way, on the temperature and the amount of rainfall and the balance of different sources of moisture in the atmosphere above. Different isotope ratios in the calcite correspond to different conditions at the surface. Each layer of a stalagmite is, in this sense, a message from the sky above, translated into stone, preserved for as long as the cave remains dry and undisturbed. Some of these cave records span hundreds of thousands of years. In European caves, the 8.2 kiloyear event leaves a visible mark, a change in the isotope ratios that corresponds to cooler, drier conditions, a brief shift, then a return to the warmer regime of the Holocene. Alongside these cave records, the pollen preserved in lake sediments tells a complementary story. Pollen grains, the tiny, almost indestructible reproductive particles of flowering plants and trees, fall into lakes and sink to the bottom, where they are preserved in the sediment. A core drilled through that sediment is a sequential record of which plants were growing in the catchment over time. And around 200 years ago, some European pollen records show a transient shift, a brief setback in the expansion of the warm climate forest, a return for a century or so to a slightly more open, cooler vegetation pattern before the forest resumed its advance. For the people alive at that time, this was not an abstract isotope signal. This was their world. The early Neolithic period, the period of the first experiments with agriculture, with the cultivation of crops and the herding of animals, was underway in parts of the Near East and was beginning to spread, slowly and unevenly, across the landscapes of Europe. Small communities were learning across generations to plant and to harvest, to store food against the winter, to stay in one place long enough to build. They were doing this in a world that, by the standards of the glacial period, was generous and warm. And then, for a century or a century and a half, the world shifted slightly. Cooler, drier in some regions, the growing season shortening just enough to matter, the rains arriving less reliably. Whether this disrupted specific communities, whether villages were abandoned, whether migrations happened, whether the spread of early farming practices was slowed, is the subject of active research and, like much in this field, of careful debate. The evidence that exists suggests that some sites in the Near East and some early agricultural settlements in parts of Europe were indeed disrupted in ways that overlap with the timing of the 8.2 kilo-year event. But the connections are rarely simple, rarely direct, and the historical record of these communities is itself fragmentary and difficult to read with the precision one would want. What can be said is that the cold snap was real, that it was sustained for long enough to affect the agricultural seasons of those living through it, and that the world into which it arrived, a world of early cultivation and tentative settlement, was one in which the reliability of the seasons was not merely a comfort, but a condition for survival. And then, as the ice records with the same clarity that recorded the cold's arrival, it ended. The freshwater pulse was spent. The Atlantic circulation, whatever form it had taken in those disrupted decades, reasserted itself. The northward transport of warmth resumed. The temperatures over the North Atlantic region recovered. The forest expanded again. The Holocene continued. But the 8.2 kilo-year event had made its point. It had demonstrated, in a way that no amount of theoretical modeling could have made quite as vivid, that the interglacial is not an unconditional guarantee, that the mechanisms which can interrupt the Atlantic circulation are not the exclusive property of ice ages, that as long as there is ice on the continents, and as long as that ice is capable of releasing meltwater in large, sudden pulses, the plumbing of the climate system retains a capacity for abrupt change. By 200 years ago, most of the great ice sheets were already mostly gone. The Laurentide was in its final stages. The Fennoscandian ice over northern Europe had essentially retreated to the mountains of Scandinavia. The ice that could feed a disruptive freshwater pulse was dwindling, and with the 8.2 kilo-year event, it seems as though the last great meltwater disruption had spent itself. The plumbing was used up, the lakes had drained. The ice margins that could have dammed another body of water like Agassiz were no longer in a position to do so. The world, after this final lurch, had somewhere to settle, and it did settle. The Holocene that followed the 8.2 kilo-year event is, by the standards of what came before, remarkably and even unusually calm. The violent swings of the glacial period are gone. The meltwater disruptions of the deglaciation are gone. What remains is a relatively gentle, relatively stable climate that has persisted with modest variations for more than 8,000 years. It is within this unusual period of calm that the entirety of recorded human history has unfolded. Every city, every writing system, every agricultural civilization, every trade network, every dynasty and republic and empire, all of it built on the foundation of a climate that happened to be, by the standards of the planet's long history, unusually well behaved. But unusually well behaved does not mean perfectly still. And here the story becomes subtler, because even within the relative calm of the Holocene, there are patterns, rhythms that are quieter than the great glacial oscillations, but that are, in their way, just as intriguing, just as mysterious. Rhythms that a researcher named Gerard Bond, working in the 1990s, began to trace through the same kind of ocean sediment records that Hartmut Heinrich had used to identify the glacial iceberg armadas. Bond was not looking initially for a new kind of climate cycle. He was looking at the distribution of ice-rafted debris, those coarse layers of sand and pebbles and lithic fragments that Heinrich had described, across a longer span of the record, extending not just through the glacial period but into the Holocene. And what he found in those sediment cores from the North Atlantic was something unexpected. The ice-rafted debris did not simply disappear when the Ice Age ended, it continued, not at the dramatic level of the Heinrich layers, not in the volumes that could be associated with great armadas of icebergs carving from the Laurentide ice sheet, but pulses of it, periodic influxes of debris, smaller and quieter than their glacial predecessors, but real and measurable and strikingly patterned. The spacing of these pulses was roughly 1/500 years, not exactly 1/1500 years. The individual intervals vary, and the record is imperfect, and the statistics of a data set that spans only 10,000 years are never going to be as robust as one might wish. But the clustering was real enough to prompt Bond and his colleagues to propose that there was a recurring cycle in the North Atlantic climate system, a roughly 1,070-year or 1/500-year heartbeat that had been operating not just in the glacial period, but throughout the Holocene. These became known as Bond cycles or Bond events. What are these Holocene Bond events exactly? They are cooler periods in the North Atlantic, punctuated by slightly greater influxes of ice-rafted material, drifting sea ice and small icebergs from Arctic and subarctic sources carrying fine debris southward. They are not the dramatic world reorganizing events of the glacial period. They are subtler, a degree or two of cooling perhaps in the North Atlantic region, a slight southward expansion of sea ice, a tendency for stormier, cooler, wetter conditions in some parts of northern Europe, drier or more variable conditions in others. The agriculture of the Holocene, the civilizations of the last several thousand years, were built in a world that was experiencing these cycles, these quiet rhythms of slightly warmer and slightly cooler, but built without any knowledge that the cycles existed. The pattern was invisible until the ocean sediment records were retrieved and read. Bond and his colleagues counted through the Holocene and identified 8 or 9 of these events, depending on how one counts and where one draws the boundaries. They are numbered, somewhat counterintuitively, from the youngest backward in time, as with the Dansgaard Oeschger events. And the alignment of these numbered events with the other records in this story produces one of those moments in science where a coincidence that is too neat to ignore demands an explanation. Bond Event 5, for instance, the 5th cooling pulse counted back from the present, aligns in time with the 8.2 kilo-year event. The cold snap, driven by the drainage of Lake Agassiz and Lake Ojibwe, coincides with a Bond cycle cooling pulse in the North Atlantic sediment record. This may not be pure coincidence. It may be that the massive freshwater discharge that caused the 2 kilo-year event was itself occurring at a time when the North Atlantic was already in a slightly cooler phase of its natural cycle, and that the two signals reinforced each other, making the 8.2 kilo-year event more severe than it might otherwise have been. Or it may be that the alignment is partly a reflection of the same underlying mechanism expressing itself in different archives. These are exactly the kinds of questions the science is still working through, precisely and patiently, one core at a time. The more recent Bond events carry a different kind of interest and a different kind of controversy, because as the numbered events approach the present, they approach territory that overlaps with recorded human history, with the patterns of documented climate variability over the last 2,000 or 3,000 years. Some researchers have proposed a connection between the most recent Bond cooling pulse and the period known as the Little Ice Age, the centuries roughly from the 14th to the 19th century, during which European winters were on average somewhat colder, glaciers in the Alps advanced, the Thames froze in winters it no longer freezes in, and harvests across northern Europe became less reliable. The Little Ice Age is not a single, sharp event of the kind the ice record shows for the 2 kilo-year cooling or the Dansgaard Oeschger warmings. It is a prolonged period of modest cooling, heterogeneous in its regional expression and its timing. But some have argued that it represents the most recent expression of the Bond cycle, the latest in a series of North Atlantic cooling pulses that have been recurring quietly throughout the Holocene. This connection is contested. Not everyone who works in this field accepts it, and the reasons for caution are legitimate ones. The Little Ice Age is a complex, multi-causal phenomenon, and the signal-to-noise ratio in the Holocene ocean sediment record for the most recent millennia is not always crisp enough to allow unambiguous attribution. The overlap with the period of increased volcanic activity and reduced solar output that characterizes some of the Little Ice Age centuries complicates any simple story of ocean-driven cycling. The debate over whether bond cycles are truly periodic, truly regular, or simply a tendency for clustering that the human mind, pattern-hungry by nature, has emphasized in reading the data. This debate remains genuinely open in the scientific community. The spacing is real in the record. The patterning is real. Whether it constitutes a strict clock, whether the intervals are close enough to 1,470 years to suggest a specific physical mechanism with a specific period, is where the certainty runs out and the questions begin. And those questions are worth sitting with rather than rushing past, because the mystery of the bond cycle pacemaker is one of the genuinely open mysteries in Holocene climate science. What drives the roughly 1,500-year rhythm? What keeps the North Atlantic cycling through these quieter oscillations, even in the absence of the great ice sheets and the meltwater pulses that powered the glacial events? Two broad classes of explanation have been proposed, and both retain scientific support, and neither has definitively displaced the other. The first points to the Sun. The output of the Sun is not perfectly constant. It varies on a range of timescales, from the 11-year sunspot cycle that even amateur astronomers can observe to longer, subtler variations in total solar irradiance that operate on timescales of centuries and millennia. Some researchers have pointed to a rough correspondence between periods of lower solar output, as inferred from records of cosmogenic isotopes like beryllium-10 and carbon-14 preserved in ice cores and tree rings, and the timing of bond events. The idea is that small but persistent reductions in solar energy reaching Earth's surface could, through a series of amplifying feedbacks, nudge the North Atlantic climate system toward its cooler phase, and trigger the kind of sea ice expansion and circulation changes that leave their fingerprint in the debris record. The second class of explanation looks inward to the ocean ice system itself. Ocean circulation is not a system that simply responds passively to external forcing. It has its own internal dynamics, its own modes of variability, its own tendencies to oscillate between states even in the absence of external nudges. The interaction between sea ice and ocean heat, between the freshwater balance of the surface and the density-driven sinking at depth, all of this can generate internal oscillations on multi-century and millennial timescales. The roughly 1,500-year period on this view is not driven by an external clock, but is a natural frequency of the coupled ocean ice atmosphere system, a resonance that expresses itself as long as the basic geometry of the ocean basins and the basic physics of the circulation remain unchanged. Most researchers today suspect the truth is a combination, that the ocean ice system has a tendency toward this kind of multi-century oscillation, and that variations in solar output, even small ones, can phase-lock the cycle, reinforce it, and help keep it coherent over many repetitions. But this remains an area of active research. The strict 1,470-year periodicity that some early studies proposed has not survived all subsequent scrutiny unchanged. The clustering of bond events is accepted. The regularity of their spacing is debated. The mechanism that drives them is not settled, which is, in its own way, a satisfying place to be. Because the honest, open question, the genuine uncertainty held with care, without either dismissing the pattern or over-claiming its precision, is exactly what makes the bond cycles so interesting to sit with on a quiet night. The cold comes back. Something in the system has a tendency to return periodically to a slightly cooler mode. The machinery is old and its gears are not fully legible to us yet. But the pattern is there in the sediment, patient and quiet, waiting for someone to read it more completely than we yet can. What we do know is that these Holocene Bond events are, in their character, fundamentally different from the glacial events earlier in this story. The Dansgaard-Oeschger jumps were violent by comparison, temperature swings of 8 to 16 degrees, accomplished in decades. The Heinrich events were dramatic in their scale, armadas of icebergs crossing the Atlantic, dropping their rocky cargo on the deep sea floor, leaving layers that Hartmut Heinrich could measure with his hands on a core in the laboratory. The 8.2 kilo-year event was sudden and specific in its cause. A lake the size of an inland sea draining catastrophically through Hudson Bay in a matter of years. The Bond cycles are quieter than all of these. They are a whisper, where the others were a shout, a periodic dimming of the same light that in the glacial period could go dark entirely. But they are part of the same story. They arise from the same ocean, the same North Atlantic system, the same interplay of fresh water and salt water, of surface currents and deep sinking, of sea ice that can retreat and advance, and in retreating and advancing, change the heat budget of a hemisphere. The Bond cycles are what happens when that system operates in a relatively quiet, relatively well-constrained mode without great ice sheets to feed it, and without catastrophic meltwater pulses to perturb it. They are the residual oscillation, the after-echo of the great glacial machinery still detectable in the sediment of the North Atlantic floor, still leaving their faint but real mark in the climate archives of the Holocene. And they remind us of something that all of the records in this story, taken together, have been quietly insisting: that the Atlantic circulation is not a fixed, static feature of the planet's geography. It is a dynamic system, one that can be weakened by fresh water, interrupted by cold, reorganized by changes in temperature and salinity that, from the inside, from the perspective of a human lifetime, might seem impossibly small to matter. The thermohaline circulations, the large-scale pattern of ocean movement driven by differences in temperature and salinity, is not a simple conveyor belt spinning at a constant rate. The image of a single loop carrying warm water north and cold water south is a useful simplification, a way of visualizing the basic logic of the system. But the real Atlantic circulation is more complicated, more layered, more susceptible to perturbation than any simple diagram can show. It has modes of operation. It can be stronger or weaker. In the glacial period, as the ice records and the sediment cores together reveal, it was repeatedly interrupted, weakened, and reorganized by the exact combination of factors we have been describing: meltwater, icebergs, freshwater caps, reduced sinking, interrupted northward heat transport. The Bond cycles suggest that even in the relatively quiet Holocene, the system retains some of this variability, not the dramatic, world-reorganizing variability of the glacial swings, but a quieter, subtler version, a tendency to oscillate, to cool slightly, and then recover on a timescale of centuries to a millennium and a half. A heartbeat that is slow enough that no individual human life could perceive it directly, but that is fast enough to leave its mark on the history of human civilizations, on the pattern of harvests and famines, on the advance and retreat of alpine glaciers, on the decades when the Thames froze, and the decades when it did not. The ice remembers all of this. The sediment on the floor of the North Atlantic remembers. The stalagmites in their dark caves remember. Each in its own language, each at its own resolution and timescale, they preserve the record of a climate system that has been oscillating, lurching, whispering, and occasionally shouting for as long as the Arctic and Antarctic have carried ice, and the Atlantic has carried salt. And the patience required to read these memories, The patience of Willi Dansgaard counting oxygen-isotope ratios in ice crystals, of Hartmut Heinrich describing the texture of sediment layers under a microscope, of Gerard Bond tracing debris pulses through core after core across decades of work. That patience is its own kind of wonder. A human timescale dedicated to reading the planet's own timescales. A lifetime spent learning to hear the rhythm of something that operates on the scale of centuries and millennia. The Bond cycles are, then, not an ending to the story of abrupt climate change, but a kind of coda. A quieter movement after the dramatic central passages. They are the climate system in its relatively stable, relatively well-behaved interglacial mode, still showing that it is not entirely still, still showing that the North Atlantic can cool and the sea ice can advance and the deep pattern can shift, even in the world we live in, even in the Holocene that has been our home for 10,000 years. And having traced the story from the great sawtooth warmings of the glacial period through the iceberg armadas of the Heinrich events, through the cold snap that settled over a warming world 8,200 years ago and lingered for a century and a half before lifting, and now through the quieter, longer rhythms of the Bond cycles that have continued in some form through the Holocene itself, having come this far through the record, there remains one more dimension of the story to lay open. One more perspective that changes the shape of everything that has come before, because all of the events described so far have been viewed, as it were, from the north. From Greenland, from the North Atlantic, from the ice cores and sediment cores that record what was happening in the Northern Hemisphere as these flips and lurches unfolded. And the picture from the north, while remarkable, is incomplete, because on the other end of the planet, something was happening at the same time, something that does not simply mirror what was happening in the north, but that contradicts it, that runs in the opposite direction. That reveals, when you hold both poles in mind at once, a machinery of planetary heat redistribution so elegant and so strange that it reframes the entire story. That machinery has a name. It is called the bipolar seesaw, and to understand it, you have to travel south, a long way south, past the equator, past the temperate latitudes of the southern hemisphere, past the sub-Antarctic islands with their permanent cloud and their colonies of wandering albatross, all the way to the continent at the bottom of the world, to Antarctica, to the ice that has been accumulating there, layer by quiet layer, for hundreds of thousands of years. The cores that speak most clearly from that southern archive are the ones drilled at places called EPICA Dome C and Vostok and Bird Station. These are not household names the way Greenland's GISPDU or NGRIP might be, even among people who follow the science closely, but they are among the most carefully tended scientific records in existence. Kilometres of ice extracted from the East Antarctic Plateau and from the West Antarctic ice sheet, each layer a page in a diary kept at the opposite end of the planet from the Greenland cores we have spent so much of this journey inside. And what those southern cores recorded during the same period we have been examining from the north is something that takes a moment to absorb, because Antarctica was doing the opposite. Not the opposite in some vague metaphorical sense, the opposite in the literal physical sense of temperatures moving in the other direction at the same time. While the northern hemisphere was locked into the long, grinding cold of the last glacial period, interrupted by those steep and dramatic Dansgaard Oeschger warmings, Antarctica was on a different trajectory. And during the period roughly between 14,500 and 12,800 years ago, a period that spans roughly 1,700 years of human experience, 1,700 years of people being born and growing old and dying generation after generation while the planet moved around them. Antarctica warmed and then paused and then cooled, not by the violent decade-scale lurches that Greenland recorded, but by a gentler, slower, more sustained shift. A long warming that ran through the coldest phases of the glacial period in the north. And then, as the world began its broader emergence from the Ice Age, a remarkable and revealing thing happened. Antarctica's warming stalled. It turned around. It dipped back into cold. This is the Antarctic Cold Reversal. And the timing of it, this is what makes it so significant. Because while Antarctica was experiencing this cold reversal, cooling back down after its long rise, the Northern Hemisphere was in the middle of a pronounced warm period known as the Berling-Allerud. A warm interstadial of some duration, recorded clearly in the Greenland cores, in European pollen sequences, in cave stalagmites from across the northern middle latitudes. The north was warming, and at the same time the south was cooling. Not because they were on different planets, not because different physical laws applied, but because of a single extraordinary mechanism that was redistributing heat between the two hemispheres and expressing its action differently at each end. Think, for a moment, of a balance beam. A long, slow balance beam with one end above the Arctic Circle and the other above the Antarctic continent. When weight is added to one end, when heat is moved toward the north, the other end rises. When the north gains warmth, the south loses it. When the north cools, the south compensates by warming. Not instantaneously, not like a light switch, but over decades and centuries, the system moves. The two ends of the beam rise and fall in opposite phase. One up, the other down, one warming, the other cooling. This is the bipolar seesaw. And it is not a model, not a theoretical prediction, not a speculation built on incomplete data. It is what the ice cores actually show when you lay the southern record next to the northern one and compare them event by event, layer by layer. The EPICA Dome C record shows it. The Vostok core confirms it. The bird station data, drilled decades before some of the others in West Antarctica, shows the same out-of-step relationship. When researchers in the 1980s and 90s began to place these records side by side, what they saw was not a coincidence. It was a pattern too systematic, too consistent, too rhythmically precise to be anything other than the expression of a real, physical mechanism operating on planetary scale. The mechanism is the Atlantic Meridional Overturning Circulation, the AMOC, the great engine of ocean circulation that we have encountered several times already in this journey, in the context of the Dansgaard Oeschger events and their coupling to sea ice retreat and heat release, in the context of the Heinrich events and the way the iceberg armadas capped the North Atlantic with fresh water and weakened the circulation, in the context of the 8.2 kiloyear event and the catastrophic meltwater pulse from Lakes Agassiz and Ojibwe. AMOC appears again and again in this story because it is the connective tissue. It is the mechanism that ties all the separate events together into a single, coherent picture. The way it connects the two poles is this. AMOC carries warm surface water northward through the Atlantic, releasing heat to the atmosphere of the North Atlantic and northern Europe as it goes, and then sinking in the Nordic seas and deep North Atlantic as it cools and becomes dense. That sinking drives a return flow of deep, cold water southward through the Atlantic, around the tip of Africa, and eventually into the Southern Ocean. When AMOC is running strong, it pumps heat northward and draws relatively warm upper waters away from the Southern Ocean. When AMOC weakens, when the fresh water caps the North Atlantic and the sinking slows, that heat pump loses power. The North cools, but because the North is no longer drawing heat northward as efficiently, heat begins to accumulate in the Southern Hemisphere. The South warms, the seesaw tilts. This is why the Antarctic Cold Reversal is the clearest single expression of the bipolar seesaw in the entire record, because it coincides not with a gradual background trend, but with a specific, identifiable period of Northern Hemisphere warming, the Bölling-Allerröd, during which AMOC was running. Heat was being pumped north, and the south was being cooled by the very efficiency of that northward transport. Antarctica was cooling not because the global climate was cooling, but because the ocean was carrying its share of the warmth away from it. And when the Bölling-Allerröd ended and the Northern Hemisphere plunged into the cold period known as the Younger Dryas, and AMOC weakened again and the northward heat pumps slowed, Antarctica resumed warming. The south gained back what the strong AMOC phase had taken. The seesaw tilted the other way. The Younger Dryas itself deserves a moment here, though it is not one of the 6 events this journey has been built around. It has earned a place as a bridge. It was a severe and relatively prolonged cold period that lasted roughly from 12,900 to 11,700 years ago, more than a millennium of cold that descended on the Northern Hemisphere just as it seemed to be emerging from the last ice age. Europe, which had been warming, grew colder again. The great forests that had been beginning to re-establish themselves shrank back. The peoples living through it would not have known that it would end in roughly 1,200 years. They would only have known that the cold had returned, that the summers were shorter and harder, that the winters pressed further into what should have been the thaw. And throughout those 1,200 years, Antarctica was doing what the seesaw required. It was warming slowly, steadily, continuing its recovery from the Antarctic Cold Reversal, accumulating warmth in the Southern Ocean while the North shivered through the Younger Dryas. And then, around 11,700 years ago, the Younger Dryas ended, and it ended fast. This is one of the most studied and repeatedly verified findings in all of ice core science. The transition out of the Younger Dryas back into the warming phase that would become the Holocene appears in the Greenland cores as a shift so abrupt that it has been described in terms of years, not decades in this case. Years. The precise duration is still the subject of careful measurement and debate, but the change is so compressed in the ice layers, the shift in oxygen isotopes, the drop in dust concentrations, the rise in snow accumulation rates, that it falls within a range that some studies place at roughly a decade or two. The diagnostic sawtooth signature of the Dansgaard Oeschger events, that steep warming limb followed by slow cooling, appears here at the end of the Younger Dryas as the last and sharpest of all the major transitions in the glacial and deglacial record. It was the beginning of the world we live in, the beginning of the Holocene, and for most of what followed, the 10,000 years or so since that transition, the climate has been, in geological terms, unusually quiet, unusually stable. The kind of stable that allowed wild grasses to be cultivated, that allowed the first mud brick settlements to persist through multiple winters, that allowed populations to grow dense enough to record their own history. The Holocene is the anomaly. It is the long exhale after the turbulent breathing of the glacial period, but the transition into it was not perfectly smooth. And this brings us to the last of the 6 events this journey set out to trace. The one that is the least famous, the least dramatic in its numbers, and perhaps the most quietly significant in what it represents, because it is the last stumble, the final lurch before the long stability began. It is called the pre-boreal oscillation. The name comes from botany, in a way, or more precisely from palynology, the study of fossil pollen. The early Holocene, the period right after the Younger Dryas ended and before the climate warmed further into what is sometimes called the boreal phase, was given the name pre-boreal by the scientists who first mapped it through the pollen sequences of European lake sediments and peat bogs. They were reading the vegetation record, reconstructing which trees and grasses were present in what proportions at each level of the sediment, and using that to infer temperature and moisture. And in those early pre-boreal sediments, in many sites across northern Europe and elsewhere, there is a brief interruption, a brief dip, a short-lived setback in the pollen of the warming climate species, a brief return of cold-adapted plants before the warming resumed. This is the pre-boreal oscillation. It sits at the very beginning of the pre-boreal zone, roughly between 11,400 and 11,200 years ago, a cold relapse of somewhere between 100 and 200 years, by the standards of the great events we have been tracing. The sawtooth Dansgaard Oeschger warmings of 8 to 16 degrees Celsius, the Heinrich events that blanketed the North Atlantic with icebergs, the 8.2 kiloyear event and its century and a half of cooling. The preboreal oscillation is a smaller thing, a flutter, a hiccup in the signal, but it is there. It is in the Greenland ice cores as a short, sharp dip in the oxygen-isotope ratio, the same D18O signal that has served as our thermometer throughout this journey, reading the temperature of the air over Greenland at the moment each layer of snow fell. It is in European pollen records across multiple sites, which is what gives it the strongest credibility as a real regional event rather than a local noise spike. And it is, almost certainly, a meltwater event, another in the long series of freshwater pulses that weakened the Atlantic circulation and cooled the surrounding region, following the same mechanism that drove the 8.2 kiloyear event, that contributed to the Heinrich events, that tied back through the whole dossier to the central role of AMOC in regulating Northern Hemisphere temperature. The source of the freshwater this time is somewhat debated. One strong candidate is the Baltic ice lake. As the Scandinavian ice sheet, the great dome of ice that had covered much of northern Europe through the glacial period, continued to melt and retreat, it had been damming water in what is now the Baltic Basin. The Baltic ice lake was not a gentle body of water. It was a large, cold, ice-margined lake, held back by the ice sheet itself and by the geography of the surrounding terrain, accumulating meltwater as the ice above it retreated. And sometime around the early preboreal, the configuration of the ice and the land shifted in a way that allowed the Baltic ice lake to drain catastrophically into the ocean, a pulse of fresh, cold, buoyant water entering the North Atlantic through what is now the Danish Straits and the connections to the North Sea, fresh enough, large enough to cap the salty surface of the ocean and slow the sinking that drives AMOC. Another candidate is continued drainage from the Laurentide ice sheet in North America, which was still melting, still releasing water through various outlets, including what would eventually become Hudson Bay. The Laurentide had been a colossal reservoir of cold water, a reservoir that had already contributed the catastrophic Lake Agassiz and Lake Ojibwe pulse that caused the 8.2 kiloyear event, and its continued disintegration was releasing fresh water into the North Atlantic system for millennia after the Younger Dryas ended. Whichever source dominated, the effect was the same in outline: a pulse of fresh water, a weakening of AMOC, a cooling of the North Atlantic region. And then, over the course of perhaps a century, perhaps a little more, the system rebalanced. The fresh water was diluted and mixed and dispersed. The sinking in the deep North Atlantic resumed. The heat pumps started pulling again. The climate warmed back to where it had been before the interruption, and then continued warming steadily into the long temperate span of the Holocene. The preboreal oscillation is the last stumble, the last time within the period this journey has traced that the system lost its footing and fell briefly backward before regaining its stride. And then, from roughly 11,000 years ago onward, the record shows something that is genuinely unusual in the context of everything we have been examining. It shows calm, not perfect, not absolute, but calm by comparison with the turbulence of what came before. The Bond cycles continued, bringing their quieter, lower amplitude pulses of cool conditions into the North Atlantic at their roughly 1,500-year intervals. The 8.2 kiloyear event broke that calm for a century and a half. There were other smaller perturbations, but the degree of variability dropped dramatically from what the glacial period had contained. The wild oscillations of the Dansgaard-Oeschger sequence, with their repeated lurches of 8 to 16 degrees Celsius in years or decades, stopped. The Holocene settled into its groove, and inside that groove, human civilization began. Not because humans had not existed before, they had. They had lived through all of it, through the Dansgaard-Oeschger warmings and the stadial cold phases between them, through the Heinrich events and their iceberg armadas, through the Younger Dryas and the Antarctic Cold Reversal and the Preboreal Oscillation. Our ancestors were present for all of these events. They gathered food, they sheltered, they made tools and art, and buried their dead in grounds that would later yield bones to careful researchers through all the turbulence that the glacial and deglacial periods had to offer. But the Holocene gave something that the glacial period had not consistently provided. It gave enough consecutive stable years for a field of cultivated grain to survive to harvest. It gave enough predictable seasons for a permanent settlement to be a reasonable investment rather than a liability. It gave enough continuity in rainfall patterns for the same river valley to be worth returning to year after year, generation after generation, until a village became a town, became a city whose name eventually made it into the historical record. The extraordinary stability of the Holocene, extraordinary in the context of what the ice cores show came before and what they show of previous interglacials, is not incidental to human history. It is the condition that made human history possible in the form we know it. And all of this, the turbulence and the calm, the lurches and the long stability, all of it is written in the ice. This is perhaps the most remarkable thread running through everything this journey has covered. Not the events themselves, astonishing as they are, not the numbers, 16 degrees in a decade, the 100,000 cubic kilometers of meltwater in a year, the armadas of icebergs crossing the open Atlantic 6 times over, the seesaw tilting between poles while the planet redistributed its heat. All of those numbers are extraordinary, but the most extraordinary thing in a way is that we know them, that human beings working with ice cores and mass spectrometers and carefully compiled databases of oxygen-isotope ratios have been able to reach back through 60,000 years, through 100,000 years, and read individual decades out of the ice. Willi Dansgaard spent decades of his career working out how to read the oxygen isotopes in Greenland snow. Hans Oeschger brought the Swiss precision and the geophysical intuition that helped turn those isotope measurements into a record of past climate, rather than just a column of numbers. Hartmut Heinrich looked at a layer of coarse sand and pebbles in a deep-sea sediment core and understood that it was the signature of something enormous, a fleet of icebergs, each one carrying its cargo of rock from the Hudson Strait, dropping its load to the seafloor as it melted in the open Atlantic. Gerard Bond spent years counting those debris layers, cross-referencing them with other cores, building the case that they recurred on a rough cycle that stretched all the way through the Holocene and into the period of human record. And the teams that drilled EPICA Dome C and Vostok and Bird Station and GISP-2 and GRIP and NGRIP, those teams worked in some of the most inhospitable places on the surface of the planet, in conditions of cold and altitude and isolation that are difficult to imagine from the warmth of wherever you are lying right now, and they brought back kilometres of ice. And those kilometres of ice became a record that no other archive on Earth can match for continuity and resolution and sheer physical presence. Because that is the thing about ice. It is physical. It is there. It is not a model, not a simulation, not an inference drawn from a chain of assumptions. It is a column of frozen atmosphere, frozen precipitation, frozen dust, frozen chemistry, laid down year by year in some cases and decade by decade in others, preserved by the cold at the top of Greenland and the heart of East Antarctica, and available, in principle, to anyone who wants to hold a piece of it in their hand. A researcher who puts a finger on a specific layer of the NGRIP core is touching the snow that fell over Greenland in a specific year during a specific decade when the air above that ice sheet was either warming toward an interstadial or cooling back into a stadial. The ice holds the answer to what that decade was like. Not approximately, not as a smoothed average blurring centuries together, as a specific, datable, measurable record of the actual conditions at the actual moment that layer was deposited. And somewhere in that column, at the depth corresponding to roughly 14,700 years ago, at the transition into what is numbered as Dansgaard, Oeschger, Event 1, the youngest and sharpest of the great sawtooth warmings, there is a layer or a sequence of thin layers that records one of the most astonishing things the planet has ever done in the space of perhaps 10 years, perhaps a single human lifetime's childhood and adolescence. The air over Greenland warmed by up to 16 degrees Celsius. The snow that fell in those layers is measurably different from the snow that fell just below it, in the cold of the younger Dryas, and measurably different again from the snow that fell just above it as the warming continued and the interstadial began. The transition is there, in the ice. Compact, physical, real. Think about what 10 years means, not 10,000 years, not a millennium, 10 years. A child born at the beginning of that transition would be approaching adolescence by the time it was complete. The world outside, with the ice sheets, the sea ice, the ocean circulation, the dust loading in the atmosphere, the methane content of the wet tropical soils, all of it was reorganizing within that child's lived experience, not in the background of geological time, where the changes are too slow to perceive even across a generation. In real time. In the time it takes a small person to learn to walk and then to run and then to begin to understand the world around them, and that child would not have known. That is the other thing worth sitting with, quietly, as this journey comes to its close. None of the people who lived through the Dansgaard-Oeschger events knew they were in one. None of the people who sheltered from the cold of a Heinrich stadial knew that somewhere in the North Atlantic, icebergs were carving from the Laurentide ice sheet in enormous numbers and marching south, dropping their loads of Hudson Strait pebbles onto the seafloor. The early Neolithic farmers, whose settlements were disrupted by the 8.2 kiloyear cooling, did not know that a glacial lake had drained through Hudson Bay and weakened the ocean circulation. The people alive during the Antarctic Cold Reversal, on whatever shores they occupied in whatever hemisphere, did not know that the planet they were standing on was tilted on a great geophysical seesaw, redistributing heat from pole to pole in slow, massive, unavoidable cycles. They lived through it. They adapted to it. They kept living. And in every case, in the case of the Dansgaard-Oeschger warmings and the stadial cold phases between them, in the case of the Heinrich events and the younger Dryas and the Antarctic Cold Reversal and the 8.2 kiloyear snap and the Bond cycles and the pre-boreal oscillation, the world recovered. Not always quickly, not without disruption, not without the kind of hardship that does not leave comfortable traces in the archaeological record, but it recovered. The AMOC restarted, the sea ice retreated, the freshwater was dispersed. The Atlantic circulation resumed its work of carrying heat northward and cold water south. The seesaw found its level again, and the climate settled, sometimes gradually and sometimes with startling speed, back into a configuration that could sustain life in the latitudes and landscapes where it had been before. The Holocene is the proof of that. The last 10,000 years of relative stability are not an accident, not a permanent condition, not a guarantee of anything in particular about what comes next. But they are evidence of something genuine and worth holding. That the system, however volatile it can be on the time scale of a human lifetime, is also capable of long periods of extraordinary calm. That after the pre-boreal oscillations' last stumble, the world found its footing and kept its balance for long enough to allow everything we know as human history to unfold. That the ice, which records both the turbulence and the calm with equal fidelity, holds both as parts of the same story. And that story is not one of chaos and meaningless lurching. It has structure. The Dansgaard Oeschger sawtooth, with its steep warming limb and its slow cooling, is a pattern, not a random noise. The Heinrich events, spaced through the glacial period at irregular but recognizable intervals, are a pattern. The Bond cycles, repeating through the Holocene with their rough 1500-year rhythm, are a pattern. The bipolar seesaw, tilting between the poles as the ocean circulation strengthens and weakens, is a pattern elegant enough to have been detected from opposite ends of the planet by comparing ice cores drilled decades apart by different teams in different countries, speaking different languages and finding that the records match, not as mirrors but as complements, not in phase but in opposition. The north cools when the south warms, the south cools when the north warms. And the agent that causes both, simultaneously, is a column of salt water in the Atlantic Ocean, sinking and rising and sinking again, moved by temperature and salinity and the slow rotation of the Earth. It is a remarkable piece of machinery. And the fact that we can read it, that we can look at an ice core pulled from the East Antarctic Plateau at EPICA Dome C, and a core pulled from the summit of the Greenland ice sheet at NGRIP, and see the seesaw expressed in both of them, antiphase, and understand what it means. That is one of the genuine achievements of the last century of science. Patient, detailed, unglamorous science conducted in extreme cold by people who were willing to spend years of their lives in places where the temperature outside could fall to -40, and the sun either never set or never rose depending on the season, in the service of a question that had no immediate practical application, but that answered something fundamental about the nature of the planet we live on. The planet keeps a diary. That was the angle this journey began with, and it is the truth this journey ends with. Not a metaphor exactly, but as close to a literal truth as science allows. The ice records what happened. Year by year, layer by layer, isotope by isotope, the snow that fell over Greenland and Antarctica preserved the conditions of its own formation. The temperature of the air, the amount of dust, the concentration of certain gases, the chemistry of the ocean moisture that eventually became the precipitation that fell on the ice sheet. And those conditions, frozen and compressed and preserved for tens of thousands of years, can be read, they can be measured, they can be dated, and they tell a story so specific, so detailed, so grounded in physical objects and measurable quantities, that the people who have spent their careers reading it sometimes describe the experience in terms that sound almost more like archaeology than physics, like excavating something that was buried, like finding a record that was always there, waiting to be understood. If you are lying down as you listen to this, if the room around you has grown dark and quiet, if the day is receding the way days do when the body is ready to let them go, then you are, in your own way, doing something the ice also does. You are settling. The ice settles too, slowly, under its own weight, compacting the layers below it, preserving what they contain. And somewhere in Greenland right now, at the bottom of the ice sheet, there are layers of snow that fell before the first pyramids were built, before the first cities were named, before writing was invented to record the names of kings and the prices of grain. Those layers are still there, still cold, still holding in their chemistry the record of the air at the moment they fell. And there are deeper layers still below those, layers from the pre-boreal oscillations' brief cold relapse, layers from the younger Dryas, layers from the great warming transition 11,700 years ago, when the last ice age finally ended and the Holocene began, the transition that may have happened in a decade or two. Layers from the 8.2 kilo-year event, when the fresh water from Lake Agassiz and Lake Ojibwe reached the North Atlantic and the circulation faltered, and a century and a half of cold settled over the warming world. Layers from the Bond cycles, their modest pulses of cooler conditions recurring through the long Holocene like a very slow, very quiet heartbeat, and deeper still, layers from the Dansgaard Oeschger events. From the 25 great warmings of the glacial period, each one a steep and startling rise, followed by a slow and reluctant cooling. Layers from the Heinrich events, layers from the Antarctic Cold Reversal, expressed in the southern ice as a slow, sustained cooling, while the north was warming during the Bölling-Allerud. All of it is in the ice, all of it is there, and a researcher with the right equipment and the right patience can put a finger on any one of those layers and say, here, this is where it happened. This is the air that was over this ice sheet in the year the climate shifted. This is the snow that fell in the decade when the world reorganized. This is the frozen record of a single human lifetime's worth of change, written in the chemistry of water at the top of the world. That is not a small thing. That is, in its way, one of the most intimate and astonishing facts about the planet we live on, that it keeps its own record, that the changes it has undergone, changes dramatic enough to reorganize the climate of entire hemispheres in the span of years or decades, are not lost, not erased, not accessible only through model projections and theoretical reconstructions. They are physically present, frozen, waiting, patient in the way that only ice and stone can be patient, which is to say without any awareness of waiting at all, and therefore with a patience that is, in its own way, perfect. Your ancestors were present for several of these events, not all of them. The deep Dansgaard Oeschger cycles of 60,000 and 80,000 years ago predate our species in some of their iterations, or predate the populations whose descendants eventually became us in the regions where the effects were strongest. But the younger Dryas, people lived through it, the 8.2 kilo-year event. There were early Neolithic communities whose farming patterns it disrupted, the pre-boreal oscillation. The early post-glacial peoples of northern Europe experienced its cold relapse, its 100 or 200 years of setback before the warming resumed. They did not know what was causing it. They did not have ice cores or mass spectrometers or databases of oxygen-isotope ratios, but they adapted, they moved, they adjusted what they hunted and what they gathered and where they built their shelters and which valleys they chose to follow when the seasons shifted. And then the world recovered, and they were still there. That is worth carrying with you if you want something to carry from this journey. Not alarm, not anxiety, not a sharpened awareness of instability or danger, but something more like perspective, the calm that comes from understanding that the world has a long story, and that the chapter we are in, however it unfolds, is not the first time the planet has reorganized its heat, or the first time the species walking around on its surface has had to find its footing in a changed landscape. The ice holds both the turbulence and the recovery. Both are part of the record. Both are real. And now the record rests. The layers accumulate, slowly, in the dark and the cold above the Greenland ice sheet, above the East Antarctic Plateau, in places where the stars are sharper than anywhere else on Earth because the air is so dry and so still. Snow falls, a layer is added, the year is sealed, and somewhere far below, older than any name you know, the pre-boreal oscillation waits in its layer, and below it the younger Dryas, and below that the 8.2 kiloyear event, and deeper still the Heinrich events with their pebbles still falling through the cold Atlantic water. And at the bottom of it all, or near enough, the Dansgaard Oeschger warmings with their steep and startling signatures, each one a decade of the whole planet breathing differently, preserved in the ice like a word, written in a language we have spent a century learning to read. If you feel moved to leave a word of your own tonight, if you want to share where in the world you are listening from, which corner of this planet you have chosen to rest in tonight, the comments are there and they are read. It is a genuinely interesting thing that people in different latitudes and longitudes, under different weather and different stars, close their eyes to the same slow story of the ice. Where you are matters. Tell me, if you like. And if this kind of journey, slow, grounded, reaching back through time into the physics of the planet itself, is the kind that helps you find the edges of sleep, there are more here. More records to descend into. More archives to open quietly, at a pace that matches the way the body slows when it is finally allowed to rest. You have done enough for one night. The ice will keep its record without your attention for a few hours. The layers will accumulate above Greenland and Antarctica in the cold and the silence, as they have been doing for longer than human memory reaches, as they will continue to do in whatever comes after tonight and tomorrow and the long run of days still ahead. Everything you carried into this hour, put it down. It will be where you left it. Lecture's over. Even the professor sleeps. Good night.